Hi guys, today what we're looking at is trigonometric functions, and we're going to be graphing y equals sine x, cos x and tan x over our domains in degrees or radians, and we're going to explore the properties and graphs and transformations of our trig functions, including amplitude, period, phase shift and asymptotes. You'll feel successful today if you can draw a sketch of the trigonometric functions y equals sine x, y equals cos x and y equals tan x. If you can identify amplitude, period, maxima, minima and asymptotes, and if you can describe horizontal and vertical transformations, and you can determine the domain and range of trigonometric functions. So we can use our unit circle to sketch the trigonometric functions y equals sine x, y equals cos x, y equals tan x, and y equals tan x, we need to remember in which quadrant sine, cos and tan are positive and negative, and how we do that is using our all stations to central. So what we have is we are going to look at a sine function first, which is y equals sine x. We're going to complete our table of values for y equals sine x in degrees first. We're going to look at what the graph looks like in degrees, and then we're going to convert that over to radians. So when we have sine x equals 0, we get 0. Sine x equals 90 is 1. Sine of 180 is 0. Sine of 270 is negative 1, and sine of 360 is 0. This is because if we were to look at our ASTC symbol a little bit in more depth in regards to our degrees, what we have is that when we are at 90 degrees, we are between our all and our sine quadrant, where sine is positive, whereas when we're at our 270 degrees, we're between our T and our C quadrant, where it is negative. That helps us out a little bit. So when we sketch our sine graph, we need to make sure that we have our y having a maximum of 1 and a minimum of negative 1. And what we do is we start at 0 degrees at 0, 90 we go up to 1, at 180 we're at 0, at 270 we are at negative 1, and at 360 we are at 0. And so from here we then sketch a nice smooth curve going through our points, and that is our graph y equals sine x over our domain of 0 to 360. Now we know that 180 degrees is equal to pi when we are looking at our radians. So what we have is that this matches up. So pi on 2 is 90, 3 pi on 2 is 270, 2 pi is 360. So that means when we have 0 in radians, we have sine of 0 is 0, sine of pi on 2 is 1, sine of pi is 0, sine of 3 pi on 2 is negative 1, and sine of 2 pi is 0. Now you can just chuck that into your calculator to get those values. We're going to put our 1 and our negative 1 on our y-axis. We're going to plot our key points like so, and we're going to sketch our nice smooth curve through our sine function y equals sine x. Now, drawing our graph gives a smooth wave curve, and as we go around the unit circle and graph the y values of the points in the unit circle, the graph should repeat itself every 360 degrees or 2 pi. So what we have here is that we have our domain of our function y equals sine x is actually negative infinity to infinity. As it goes on forever, we're just asked to draw it in restricted domains, such as 0 to 360 or 0 to 2 pi. Our range of our function is our y values, and our range is the lowest y value of y equals sine x is negative 1, and our largest y value is 1. And now this is an odd function. So if we were to look at our function for over our domain of negative 360 to 360, we're going to see that if we turn our page and flip it, it's exactly the same function, and it's symmetrical about the line y equals negative x. Okay, so if we have a look at sketching this, we have 1, negative 1 for our y values. We can even do it at 3 values up if you prefer. It doesn't matter as long as you're nice and consistent. So we start at 0, at 90 we're at 1, 180 we're at 0, 270 we're at -1, and 360 we're at 0. And so we have that familiar graph that we drew up above. And then we do the opposite the other way. So at -90 it's at -1, at 180 at -180 it's at 0, at -270 it's at 1, and at -360 it's at 0. And so we get our nice smooth sine curve over that domain of -360 to 360. Okay, moving on to our cosine function y equals cos x. Now, when x equals 0, we have that it is equal to 1. When x equals 90, we have that y equals cos 90 is equal to 0. When y equals cos 180 is equal to -1. When y equals cos 270, it's back at 0. And at y equals cos 360, it's back at 1. So putting I'm going to go up 3, I think, 1 and -1 on there. We start at 1, back down to 90, down to -1 at 180 degrees, back to 270, and then up to 360. We can sketch our cos curve, keeping it nice and smooth. That wasn't very smooth. Let me start that again. Oh, that didn't go through 90. Like so. Okay, our y equals cos x for our domain of 0 to 360. We can also graph it in the domain of 0 to 2 pi. That's where when x is 0, y is 1. When x is pi on 2, y is 0. When we have x is pi, we have cos of pi is -1. Cos of 3 pi on 2 is 0. And cos of 2 pi is 1. So when we substitute in our 1 and our -1 onto our y-axis, we get the exact same curve that we had when we sketched our function in our domain in degrees. But now it's our domain in radians. And that is our function y equals cos x. So drawing the graph gives our smooth wave curve again. And if we look at the graph and the table of values, we might notice that the cosine function is actually our sine function, just translated 90 degrees or pi on 2 to the left. So as we looked at in a previous lesson about complementary angles, we had that cos x equals sine x plus 90 or sine x plus pi on 2. So as we go around the unit circle and graph the x values of the points of the unit circle, the graph repeats itself every 2 pi or 360 degrees. This means our domain of our cos function is -infinity to infinity. Our range is -1 to 1, and this is symmetrical about the y-axis, so this is an even function when we're looking at y equals cos x. Now, our last function that we have to look at is our tangent function, y equals tan x. So we want to complete the table values of y equals tan x. So when we have x equals 0, we get that tan of 0 is in fact 0. When we substitute in 90 degrees, we get a math error in our calculator. That tells us that we have an asymptote at 90 degrees. I'm going to draw that in straight away. When we substitute in 180 degrees for x, we get 0, 270, we get a math error, and 360, we get 0. So we have another asymptote at 270 degrees. Now, what we have for our tan function is we have little cubics in between these domains, like so. with our intercepts of our x-axis at 0, 180, 360 degrees. So the same thing happens when we're in our radians, okay? We know that 180 degrees is equal to pi, so we have our same asymptotes at 90 degrees, which in this case is pi on 2, and at 270 degrees, which is equivalent to 3 pi on 2, and then we have our asymptotes like so. Now, we looked at how to sketch these trig functions back in year 10, so I'm hoping that you are familiar with them. So we have an undefined for x equals 90, which is pi on 2, and x equals 270, which is 3 pi on 2. So we have our vertical asymptotes at those x values where the function is discontinuous. As we go around the unit circle and graph the values of y on x at the points on the unit circle, the graph should repeat itself every 180 degrees or pi. So our domain for our tan function is negative infinity to infinity, except when x equals 90, 270, I think the next one's 540 degrees, if you're looking degrees, or do pi on 2, 3 pi on 2, 5 pi on 2. Our range is from negative infinity to infinity, and as this is a cubic, it's an odd function for our tan function. Now, they are our three parent curves for our sine function, our cosine function, and our tangent function. Now, it's really important that you know what those three parent functions look like when we are going to now have a look at translating them and our properties. So, all trigonometric functions repeat at regular intervals. That's why they are called periodic functions. Okay, so what we have is we have periodic functions. We are talking about our period to start off with. So the period is the length of one cycle on the x-axis before the function repeats itself, e.g. at 360 or 2 pi for our cos and our sine functions. Now, period is a horizontal dilation where y equals a on x has a scale factor of 1 on a. So what this means is that when we have y equals sine a of x, it has a period of 2 pi on a. When we have y cos a of x, it has a period of 2 pi on a. And when we have y equals tan a of x, it has a period of pi on a. Now, if a is greater than 1, it means that the function is compressed horizontally. If 0 is less than a is less than 1, the function is stretched horizontally. If a is equal to negative 1, the function is reflected in our y-axis. Fun! The next one that we are looking at is our amplitude. So when we're looking at our amplitude, it is the height from the center of the periodic function to the maximum or minimum values. Amplitude is a vertical dilation where y equals kf of x with a scale factor of k. So for y equals k sine of x, y equals k cos of x, they have both got amplitude k, whereas y equals k tan of x has no amplitude due to its range, because its range is negative infinity to infinity. So multiplying our function by any value of k is not going to affect it. Now, if k is greater than 1, the function is stretched vertically. If 0 is less than k is less than 1, the function is compressed vertically. And if k equals negative 1, the function is reflected in the x-axis. So remember, our amplitude is the distance from our center of our function to the maximum and minimum point. And because there is no maximum and minimum points for tan, we have no amplitude. The k value does still affect the graph, making it skinnier or wider, but we don't have that. It is going to affect it a huge ton. Now, when we have y equals sine x, y equals cos x, and y equals tan x, we have our period and amplitude for those three functions. Then when we have y equals k sine of ax, y equals k cos of ax and y equals k tan of ax, we have our amplitude for those three general functions and our period. Okay. All right, what we're going to look at is some examples here. So for each function, we're going to sketch each function in the domain of 0 to 2 pi. So we're working in radians, and we're going to state the period and the amplitude. So if we're looking at our period and our amplitude. So our amplitude is the value in front of our function. So in this first one, y equals 5 sine x, that means that our amplitude is going to equal 5. So it is not changing our shape of our sine curve horizontally, only vertically. And we have that our period is going to be 2 pi. Now, the reason why it is 2 pi is because our a value, so we have a k value equals 5, and we have our a value equals 1. And when we're finding our period, it is 2 pi on a, and our a value is just 1. So what we're going to do is on our y-axis, we're going to say that is 5 and that is negative 5. We're sketching sine, so sine starts at 0. And at pi on 2, it's going to go to its maximum point at 5. Pi, it's at 0. 3 pi on 2, it's at its minimum point of minus 5. And at 2 pi, it's back at 0. So we can then sketch our curve like so. Y equals 5 sine x. Okay, looking at B. With B, what we have is y equals sine 4x. Now, our amplitude is pretty straightforward here. We have that k equals 1, so that means that our amplitude is going to equal 1. But with our period, what we have is a 4 for our a value. So a equals 4. So remember, our period is 2 pi on a. So our period is going to be 2 pi over 4, which is equal to pi on 2. So we're going to be repeating ourselves every pi on 2s. Now, our amplitude is 1, so we're just going to go up 1, down to minus 1. Just done 3 boxes. What this a value also tells us is how many repeats. So what we have is that we are going to have that our curve is repeated, or our function is repeated 4 times. So what that means is we're sketching sines, it starts at 0. We want it to be back at 0 and going to start again at pi on 2, pi, 3 pi on 2, and 2 pi. So they're the 4 places where it's going to start again, meaning that it has 5 intercepts, key intercepts where it's about to start again. So what we want to do is we're going to have to sketch a small curve between 0 and pi on 2. So it's going to go up at 0, it's going to come back at pi on 4. So actually at pi on 8 is where it goes up to hit 1. Then we're down here and then we're back. So there is our first period there. Now we just have to repeat this 4 times so that our period is then pi on 2 for our domain of 0 to 2 pi. So we go up, down. So we can just continue the pattern of up, up, down, down until we get it. And then we draw a nice smooth curve going through our function to get our y equals sine 4x. See how that has repeated once, twice, 3 times, and finally a 4th time through on our domain of 0 to 2 pi. Okay, looking at the next two, it's combining 2 at a time, so 2 different transformations, whereas the first one was an amplitude, the second one was a period. So in C, we have y equals 5 cos 3x. So what we have is our amplitude, or our k value. It's easiest to spot. Our k value equals 5. So that means our amplitude is going to equal 5. Whereas our period helps us find our a value. Our a value is 3. So our period is going to be 2 pi on a. So 2 pi over our a value of 3. And we can't simplify that any further. So just remember that we have 2 pi on our a value. So remember, what this means is our a value means it repeats, our curve is going to repeat 3 times. We also have our amplitude of 5. So we're going to put 5 up there, minus 5 down here. And we want it to repeat 5 times when we get to 2 pi on 3. Now, if we're trying to work out where 2 pi on 3 is on our curve, what we have is this is broken up into pi on 6s. So between 0 and 2 pi, it's broken up to pi on 6. So we have that there is pi on 6, pi on 3. We'll then have pi on 2. This is 2 pi on 3, so that's where it's going to first repeat. And then we'll have 5 pi on 6. Does that make sense? So then what we'll see is we've got... Yeah, cool. So we are sketching cos this time. Now, cos starts up at the top of the amplitude and it comes down, bottoms out, and then it comes back. So at this point up here is where we're going to repeat. So what we have is we've broken it up so that we have our 4 spots between our graph. So then we're going to sketch this another time. So we go down, across, and up. So that's our second go through. We need to do this one more time. So down, across, and up. And so we can see that we have our 3 repeats. Now, we don't necessarily need our values on there, but by breaking up into pi on 6s, that helps us to work out what is going on along our axes. So what we do is whatever our period is, so it's 2 pi on 3, I believe if we divide it by 4, we get, if our period is 2 pi on 3, we divide it by 4 to get our values along our x-axis. Whereas when our period is 2 pi, when we divide that by 4, 2 pi divided by 4, that's pi on 2. So that tells us that we want to go pi on 2 across. So let's just write a little note. So note, divide period by 4 to get x-axis increments. I don't think I spelled that right, but you get my gist. Okay, the last one, D, for our period and amplitude. For this one, we have our amplitude is 2, okay, but technically there is, so K value equals 2, but technically there is no amplitude because we have a tan function. And our period, what we have is we have A equals a half. So our period is 2 pi on a half, right? Which is, period. Sorry. Period is pi on A when we're talking about, so period equals pi on A when we're talking about our tan function. So it's pi on a half, which just equals 2 pi. So what this means is that we're stretching our graph out And so we only want from what happens between 0 and pi to now occur between 0 and 2 pi. So this a value means we want it to only repeat half the time. Does that make sense? So we don't want it the whole thing. So what we're going to have is, instead of, normally our asymptote is at pi on 2. So now our asymptote is going to stretch out to be at pi, and we're going to have that our function has that part there and this part like so. Oops, and I forgot to highlight how we got our a, which is a half. Okay, that is our period and our amplitude. Now we're going to look at our center of our trigonometric functions. The center of our trigonometric functions, of a periodic functions, is its mean value, and it's the point that is equidistant from the maximum and the minimum values. The center of the mean value of y equals sine x, y equals cos x, and y equals tan x is 0, represented by our x-axis. Our center is a vertical translation where we have our c value moving our graph up or down. So the center of y equals sine x plus c, y equals cos x plus c, and y equals tan x plus c is c is greater than 0, then it's translated upwards. If c is less than 0, then it's translated downwards. Excuse me. So if we're looking at sketching y equals cos x minus 2, that means our center is now going to be at minus 2. So I like to draw in a little, not an asymptote line, but a line at y equals 2, which is now our center. And so what we have is we have our amplitude is going to be 1 because our k value is 1. Our center here is minus 2. So we have c equals minus 2. I could write that down below. Center is minus 2. We have our period. There's nothing in front of our a. So we have our a value equals 1. This is a cos function. So period is 2 pi on a, which is 2 pi on 1, which is just 2 pi. And then what we have is to get what happens to our values. So we've decided that this is where minus 2 is, minus 1, minus 3, is that our cos function starts at our maximum point. So our maximum point, we have now shifted our graph down, our maximum point is minus 1. So then what we're going to do is we're going to go through pi on 2 at minus 2, where our new center is. At pi, it's at minus 3. At 3 pi on 2, it's back to our center. And at pi on 2, it's back to minus 1. So we can then sketch our cos function like so. Nice and smooth. To get our curve y equals cos x minus 2. So we've shifted our graph down to units. Now our next one here, we have y equals sine 2x plus 1. So we have our k value is equal to 1. We have our a value is equal to 2. And we have our center is equal to 1. So our center is 1. Our period is going to be 2 pi on 2, which is equal to 2. So remember, that means that we are repeating, 2 pi. No, it's not equal to 2. It's equal to pi. So that means we have 2 repeats in our domain. And our range, we didn't answer our range for our last one. Our range was minus 1 to 1 originally, but we've moved that down to, so our range is now minus 3 to minus 1. Okay, sorry, now back to B. Far out. We have that we need our 1. We can, because our, we're going to put 1 here, 2 here, 0 here, obviously. We have our center is at 1. That's our center. And we have that it's going to repeat. This is the wrong axes. Because if we divide pi by 4, we need pi on 4. So pi on 4 is going to be directly there. So pi on 4, that's where 3 pi on 4 is. 3 pi on 4. Here, 5 pi on 4, and here is 7 pi on 4. So what we're going to do is sine. We need to fit it all in. First one in, we need to fit one repeat of it between 0 and pi, and the second one between pi and 2 pi. So for sine, we start at our center. So we start at 1. Oh, that's the eraser. We start at 1. Then we go up. Then we go down to the center. Then we go down 1 to our minimum value and then back. There's our first repeat. Ready to start again. Okay, so now we do start again. So at 5 pi, we're up there. 3 pi and 2, we're here. 7 pi and 4, and then 2 pi. Then we repeat it like so. And that's our beautiful graph of y equals sine 2x plus 1. Remember, 2 means that we have 2 repeats of our graph. So we've gone started here, finished here, started again. Okay, our center's at 1, so we've shifted our graph up 1. And yeah, so then we can see that our range, we've added 1 to our range. So we've got our range is now 2. Nope, it's 0, 2, because we write our smallest value first. 0, 2. Okay, so if we're looking at how to work out our range, what we have is that with our range, we have that it's -1 plus our center and 1 plus our center. Does that make sense? That helps us to work out our range. That helps us to work out our maximum value, our minimum value as well. Okay, center's meant to be easy. The next one is our phase shift. So, and I believe this is our last 2 examples. Amazing. So we have our phase shift of our trigonometric functions. So the graphs of trigonometric functions can change their phase. Phase is a horizontal translation where y equals fx plus b. We have b is moving the graph left or right. So we have our phase shift is b for y equals sine x plus b, y equals cos x plus b, and y equals tan x plus b. Now, if b is greater than 0, it's translated to the left. B is less than 0, the phase shift is translated to the right, same as our horizontal translation. So we're going to sketch the graph of each function in the domain of 0 to 2 pi and state the phase, shift, and period. So with this one, our period is what's in front here. So our a value is equal to 1. Our k value is 1. So it's does that make sense? Our k value is 1. So we're going to have that. We're up at 1, down at -1. And we have that our phase shift is plus b. So we're going to have, if our phase is b equals pi on 2, we're going to move this pi on 2 units positive, so to the left. So we're going to pick up our original function and move it to the left. So that means that if we're picking this up and moving it to the left, we are really going to be starting our curve. Our normal sine curve would be starting over where our minus pi on 2 is. So we'd start it here and we go up like this and then go down and then, does that make sense? So what we're doing is we're pretty much going to sketch that graph, but just within the domain of 0 to 2 pi. So we don't want, we don't want what's going on over here. Does that make sense? So we just want the pink graph that I've perfectly sketched. And because our a was 1, we have that our period is 2 pi on 1, which is just 2 pi. Because when we're finding period of a sine function, it is 2 pi on a. That looks great. So I'm not going to redo that, but it is our function y equals sine x plus pi on 2. Our last one, we have y equals tan x minus pi. So again, our k value, well, it's tan, so amplitude doesn't matter, but our k value is equal to 1. Our a value is what's in front of outside of our bracket, which is our A equals 1. Now, period for tan is pi on A. So that means we'll have pi on 1, which is equal to pi. Amazing. And then we have that our B value is -1. Negative pi, sorry. So we're going to be moving pi units to the right. So what we normally have is to not graph this. This is just a little visual. So we normally have our asymptote here and here. We are going to pick those asymptotes up and move them pi units to the right. So we're going to, when we're moving to the right, we're moving in this direction. They just stay where they are. Surely not. Maybe they do. I think they do. Let's just double check this. So they move to the right pi units. Yeah, so they're just actually going to stay where they are. So we can just draw on top of them, I believe. Y equals tan x minus pi. Settings x pi. Okay, yeah, our asymptotes stay. Wow, how cool. So they stay where they are. And then we're just picking up our normal curve. So I'm just going to go over them then. And it's literally just our normal curve because it has a period of pi. Oh my goodness. So it's literally just our normal curve. Like so. Because if you think about it and you pick this up and you move it. So if we were to actually, sorry, in case you need a visual like I do right now, if you pick this up and you move it pi units to the right, so we go all the way to the right pi units, we get this, right? Sorry that it moved. We get this. And so then we just want to draw in what's happening, what should be happening on the left. And because it is a periodic function, it's just what was happening before. Like so. Revolutionary, honestly.